Hello, guys. Getting near the end. So this really sort of builds off of, well, a little bit at least. This first part builds off of what we talked about with radioactivity, um, which is again a spontaneous event that in which a heavier nucleus breaks up into smaller stuff. Well, in this case, we're just going to talk in general about any nuclear reaction. The big deal is that you have to conserve both charge and mass. Right? No brainer there. So, in a simple example like this, we start with helium. What pops up? Do I pop the stuff in? Yeah. Two protons, two neutrons. And let's say this is nitrogen 14. Well, it turns into something and, well, a proton. So what's the something? All we have to do here is do the math. There were 18 mass units before. There must be 18 now. So X must have, I know this is supposed to be on the left, 17 protons, and we had 17 neutrons. We had 9 protons before. We have to still have 9, so that means there are 8 here. So what's 8? That's oxygen, right? So that's, oh yeah, okay, that's oxygen. Now, yeah, you will not be responsible for knowing, you don't have to memorize the periodic table, but you certainly should be able to, figure out how many nucleons are in any reactant. Okay? All right. Now, we're going to start to talk about, when we really say like, 2, or, well, really, I guess this 4, really represents like, we say there are 4 units of mass. Well, these units are, that's pretty much a rounded number. It really is a rounded number. And, that 4, well, 4 what? It's really close to 4 what we call unified mass units. The unified mass unit is an actual unit of mass, right? And it's a real small one, right? So we can say that a proton has about 1 unit, well, 1 unified mass unit worth of mass. So, yeah, just to say 4, though, for us isn't precise enough anymore. We're going to start to get a lot more precise. And we're going to define the unified mass unit as the mass of 1/12 the mass of a carbon-12 nucleus. All right? Just like, well, I don't know if you really remember what a mole is, but a mole is the number of elementary particles in 12 grams of carbon-12. Why all this carbon-12 talk? I think just because it's really the most abundant and easily and the most easily studyable atom. All right, there's tons of carbon-12 everywhere. So we just say, okay, let's call that. Let's base everything off of that. All right, if the mass of 12 grams, or sorry, if we use 12 grams of carbon-12, well, we call that 1 mole. All right, and how many particles is that? That's Avogadro's number, 6.02 times 10 to the negative, or sorry, to the 23rd particles. So anything that's that number of particles, we call a mole. All right. The unified mass unit is just, if carbon-12 is defined to be, have a mass of 12.00000 grams, then the unified mass unit is 1/12 of that. All right. So with that in mind, we can start to be a lot more precise, and we're going to need to be more precise about actual masses of things, right? We say that protons and neutrons have a mass of quote-unquote 1. Well, if we talk about unified mass units, they really have masses that are different than 1, right? And there's our quote-unquote massless electron, yeah? And that's, well, a really small number of unified mass units, okay? What starts to get interesting is, if we say that the atomic mass of um, carbon-12 is 12 on the nose unified mass units, right? That's kind of the definition. Well, if we look at this of its parts, all right, we say, well, there's actually, right, 6 protons, where we could say the mass of those, if we did 6 times the mass of a proton, grab my calculator. Well, that's 6 times 1.007276. Well, that's 6.04366 unified mass units. And then there's 6, I shouldn't have changed colors, 6 neutrons. So if we do 6 times the mass of a neutron, that's 6 times 1.008665. That's 6.05199 unified mass units. And I guess 1190. We want to keep those sig figs. And then there's electrons, of course. There's 6 electrons in carbon-12. So 6 times the mass of an electron, 6 times 0.0005486. Different number of sig figs for whatever reason. Whoops. 6. Insert times that. Oh, come on. 6 times. Okay, and then we get 0.0032916. Well, you may notice that if we were to add all these things up, that's more than 12. Right? And the part that we really need to focus about is really the nucleus only. So if we did the mass of the nucleus, I'm going to say it's that 12 unified mass units minus the mass of the electrons. All right, or really I'll do it like that, because there are 6 electrons. All right, so if we do 12 minus that, that's 12 minus our 0.0032916, and that's 11.99678 unified mass units. Well, clearly, the sum of this and this, the sum of the nuclear components, is a lot more than that, right? So if I take these two, well, not a lot. If I take these two numbers and add them up, 6.04365 6.04366, just checking, plus 6.05199. That gets me, I'm going to do this, mass of the parts, which is really 6 proton masses plus 6 neutron masses. Well, that's 12.095646 unified mass units. So there's a difference. There's a difference between the mass of a nucleus and the mass of its parts, which hopefully is a little bit strange, seems a little bit strange. All right? And this difference, if we took this difference, it's called the mass defect. Every nucleus exhibits, demonstrates, shows, has what we call a mass defect, where the sum of its, or the sum of the masses of the parts is more than the mass of the combined parts, which seems strange. All right, so there we go, next page. Now this you'll end up using at some point, a little reference I included for you. And yeah, so every nucleus exhibits what we call a mass defect. Okay, so if we have element X with Z number of protons and A number of nucleons, all right, if we want to find mass defect, here's the first thing you always have to do. First, we want the mass of the nucleus only, what we call the bound mass. That's the stuff all together. All right, and so what we have to do here is we have to take the atomic mass, right? Atomic mass includes protons, neutrons, and electrons. We have to get rid of the mass of the electrons. So that means we need the mass of, nucleus only. So I would do here, well, M atomic minus m of electrons. So I'm going to write this as, again, m atomic. Well, what's the mass of the electrons? Well, it's, if we assume that, yeah, here we go. Assume number of electrons is equal to number of protons. Assume that they're neutral elements, or atoms, I should say. So Z is the number of protons, also the number of electrons. So there's Z number of electrons times the mass of an electron. Yeah? Make sense? Okay. So that gives us our bound nuclear mass. Ooh. Let me do this. So I'll just write that as one thing here. M atomic. I'll write it in blue so it's matched up. M atomic minus Z times the mass of an electron. Okay, now we want to find the mass of the unbound nucleons. Okay, I don't know why I underlined the ons there. Oh well. I guess as opposed to nucleus. So this is going to be, well, the unbound mass is the mass of all the parts by themselves. So that's going to be, well, however many protons you have times the mass of a proton plus however many neutrons you have. Well, how many neutrons do you have? That's what we call A minus Z, right? Because this is total number of nucleons, right? This is number of protons. So number of neutrons is A minus Z. I'm hoping everyone's comfortable with this being number of protons, atomic number, this being number of nucleons, total, nucleons are anything in the nucleus. All right, so A times Z times the mass of a neutron. That's how we find the unbound mass. Okay? Well, calculate the mass defect. That's going to be M unbound minus M bound. All right, just take the difference. You'll get an answer in unified mass units. Okay? You jerk. Yeah. So I think we have an example here. Sure. Let's find the mass defect of an alpha particle, a helium nucleus with that given mass. Okay, well, what's nice is we've already been given the bound mass. This is our M bound. That's 4.001506 U. Now we want unbound. So if we do, that's going to be, let's see, 2 protons plus 2 neutrons. So let's see, M unbound. Now go back a couple pages to find those masses. Ooh, I might have to do that myself. Let's see. Go to slide 19. Come on. Hang on, I'm just going to write this on the board. Okay, so here, I wrote them down. So if we do this, let's see, the bound mass, 2 times the mass of a proton, 1.007276 plus 2 times 1.008665 mass of a neutron. I get 4.031882 unified mass units. So if we want the mass defect, what we call delta M, that's going to be mass unbound minus mass bound. Out of the way. Out of the way. Well, that's going to be delta M is, let's see, minus 4.001, oops, 1506. Well, 0.0376. What? Oh, 0. I'm a jerk. 0.0306 There we go. There's our mass defect. Okay? We'll talk about what the significance of that is in a moment. Now, the big deal here is, an alpha particle is really already just a nucleus. So notice we didn't have to do this part yet. Right? We didn't have to take off the electrons because an alpha particle doesn't have electrons. Helium does have electrons, but an alpha particle is just the helium nucleus. So we didn't have to do that. All right? In this thing that I want you to do at some point, whether it's, well, probably not right now, but yeah, at some point, find the mass defect of neon 20 and calcium 20. Those are atoms. Okay? So make sure, don't forget, well, step one. Don't forget step one. Do this first. All right? Make sure we're doing that. All right? Remove the mass, subtract the mass of the electrons. Okay? Okay. Now, yeah, what's the deal here? Why is there this difference? What is this mass defect? What significance does it have? Well, the special theory of relativity, come on, keep going, there you go, says that this mass, this difference in mass, really is equivalent to a certain amount of energy. We finally get to use E equals mc squared, right? And we say that the amount of that mass defect really accounts for what we call the binding energy of the nucleus, right? The amount of energy that's holding together the nucleus. Or really we can say that the binding energy is the mass defect, right? This is mass defect times c squared. Now, we are going to find our binding energies in typically in MeVs, mega electron volts. So we are going to use c squared is 931.5 MeV per U. All right, now I also have, this is another little extra assignment. If we say that C can be expressed as 3 times 10 to the 8th meters per second, well, I'd like you to prove somehow that, that c squared, written in different units, is the same as 931 MeV per U. Or really we're saying that 9, because here's c squared, times 10 to the 16th meters squared per second squared is the same as 931.5 MeV per U. All right, I'd like you to prove that. It'll take things like, oh yeah, I know an EV is 1.6 times 10 to the negative 19th joules, and joules gets me closer to things like meters and seconds, right? And then a U, a unified mass unit, well, you gotta, find a conversion for that, right? For example, if we know a mass of an electron in U's and we know it in kilograms, that gives you a conversion factor between the two, okay? So go through that little exercise, prove that, all right? So the only next step here is we can now calculate binding energies for atoms, for nuclei, right? If we just take the mass defect and multiply by our value here of c squared, all right? The last little step is that we can find binding energy, what we call per nucleon, right? So if we do that, let's do that over here. E binding per nucleon is just going to be E binding divided by A, right? Where A is the number of nucleons. All you have to do there is no big deal. Just divide by the total number of nucleons once you get your binding energy. Okay? So here's two more things to do. Find the binding energy per nucleon of these two atoms. These are atomic masses. Okay? These are atomic masses. So remember, first step, subtract the mass of the electrons. Okay? Which means, yeah, you actually have to find atomic number for gold and whatever NB is. All right? Number of protons. I don't know that off the top of my head, but I'm sure you can access a periodic table somehow. All right? Yeah, this podcast here The link seems to be dead, which is too bad. It was a quick little thing, but it was pretty interesting. I think that's the end of where we're going today. Yeah, we'll start next time with fission and fusion. Okay, so you should have enough to do for a while, right? Some mass defects from the last page, this little dealio here, that conversion, and then finding these binding energies per nucleon. Okay, I'd like those submitted before you leave today. That's for you guys, Block 4. Block 1, that's homework due when I see you on Monday. Okay? Thank you, and I will see you soon. Oh wait, don't end show yet.